Okay, in this second example, we're being asked to graph 5x times e to the x. Now, you wouldn't be expected to actually know what this looks like before you graph it. We know what e to the x looks like. It's got this kind of shape. And e to the x is quite a powerful curve. So there's probably going to be something similar in the solution, something similar to that shape, but not exactly the same. Okay, so let's start by finding the derivatives. So the first derivative, now we've got to use our product rule. So u equals 5x, du dx equals 5, v equals e to the x. So dv dx is also e to the x. So the first derivative, remember, is, as it is on the formula sheet, it says u times dv dx, so 5x times e to the x, plus v times du dx, so e to the x times 5, or 5e to the x. You can also factorize that. They've both got a 5e to the x. So that one also has an x, that one's plus 1. And then we want the second derivative. Now this is actually a nice easy one to find the second derivative for if you go from this first line, because this is the same as the original function, so we already know what the derivative is for that. The derivative for that is all of that. So I'll just write that again. And then I also need the derivative of this piece, so that is the derivative of that, plus the derivative of that, which is also 5e to the x. I'll just simplify that a bit. 5e to the x plus 5e to the x is 10e to the x. So 5x e to the x, plus 10e to the x, and then factorize out 5e to the x. So 5e to the x. So here we've also got an x, and here we've got 2. Okay, so those are our first two derivatives. Okay, so firstly, let's consider stationary points. So the stationary points are where the first derivative equals 0. So we're 5e to the x, x plus 1 equals 0. Now, e to the x never equals 0. So that's only going to be when this bracket equals 0. So in other words, where x equals minus 1, there is a stationary point. Let's find the y-coordinate for that by putting it back into our original function. So 5 times minus 1, e to the minus 1. 5 times minus 1 is minus 5. Use our index laws. Minus 1 means 1 over, doesn't it? So that's over e to the 1, or just e. If you did put that in your calculator, it equals negative 1.84 to 2 decimal places. Okay, let's find the nature of that stationary point by putting it into the second derivative. So the second derivative at negative 5 on e, if I put that in, I am going to get, where is it here, second derivative, 5 times e to the negative 1.84 times negative 1.84 plus 2. And what you're going to get there is a positive number. Okay, so it's a minimum. Okay, so we've found our stationary point. Now let's find any points of inflection. So where does the second derivative equal 0? So the second derivative equals 0 will only happen when this bracket is 0. So it's going to be x equals negative 2. Okay, so there's a possible POI at x equals negative 2. Let's do a second derivative test to see if it is one or not. So let's go negative 2.1 and negative 1.9. So second derivative. If you put negative 2.1 in, you're going to get a negative answer. You put negative 2 in, you get a 0. And if you put negative 1.9 in, you get a positive answer. So concavity has changed. Okay, so we need to put that back into our original function to find the y-coordinate. So y equals 5 times negative 2e to the negative 2, 5 times negative 2 is negative 10 over, because of the minus, e squared. And that equals negative 1.35 to 2 decimal places. Now with this function too, we've got, so far we've got a minimum, we've got a point of inflection. We also need to consider intercepts and asymptotes. Let's do intercepts next. So intercepts are where the original function x equals 0, y equals 0. So if x equals 0, y equals 5 times 0, e to the 0, so 5 times 0 times 1, which is 0. And if y equals 0, now e to the x can't be 0, so it relies on 5x being 0. That gives us x equals 0. So there's only one intercept at 0, 0. Okay, asymptotes. So I'll just write our function again. Oh, f of x equals 5x e to the x. Now what we're going to do to find asymptotes is think about what happens when x gets bigger firstly. So the limit as x goes to infinity. So if you think about this function, e to the x gets really big. X gets big. So it's a big thing times a really big thing. That's going to get really big. It's going to go to infinity. Okay, you could do that by substituting in bigger and bigger numbers of x into your calculator. Even by the time you get to 1,000, it's going to give you a maths error because it's so big. What you'll see is the bigger number you put in for x, the bigger your answer is going to be. And then let's consider the limit as x goes to negative infinity. So what happens is we put in smaller values. Now I'll draw up a little bit of a table for this to show you. So if we put in, for example, negative 10 into our original function, our calculator gives us something pretty small already. If I then put in negative 100, I get something really tiny. So I can see a pattern here. It's getting smaller. To the negative 41, that is tiny, tiny, tiny. When I put in negative 1,000, my calculator just gave me 0. Okay, the numbers are getting smaller and smaller and smaller, and that makes sense. E to the x gets smaller and smaller and smaller and smaller. These are negative values, okay? So the limit there goes to 0. It will get really close to 0. It's negative, so it's just below 0. Okay, let's put all that together into a graph. Now, I do suggest you put this into Desmos as well, so you can have a look at it. So, x, y, 0. Now, so what we found, firstly, we found that there was a minimum when x equals negative 1. I'll put that there. So there's our minimum there. The y coordinate for that was negative 1.84. So that's negative 1, negative 1.84. And then we found a point of inflection at negative 2. Now the y coordinate at negative 2 was negative 1.35. So let's put that about there. And that was a point of inflection. We found that as we got smaller, the curve went closer and closer to 0. Let's have a look at what happens here. So this is the only point of inflection. So concavity can't change anywhere other than at that point. To the right of that point, we had a minimum. It's concave up. Remember, it also goes through 0, 0. So we're going to get that shape, and then it's actually just going to keep going up. It can't come back down because there are no more stationary points. It can't change concavity because there are no more points of inflection. It has to just keep going. Now this is a point of inflection, so after that it's going to be concave down. And we found that it gets closer and closer and closer to 0, but never touches 0. So there is a horizontal asymptote there at 0. And that's what the curve looks like.